Hello, welcome to all for this video lecture on basic electronics. Let me have a quick review what we have covered in the previous class. In the previous class, we have discussed collector characteristics curves, which is shown here, and we have discussed even a problem related to the collector characteristics curves. Now it's the time to discuss two important regions of operations, namely cutoff region. Let's try and take it right here. Namely cutoff region and saturation region. Okay, the saturation region. So these two regions we'll discuss in today's class. So let's first focus on the cutoff region. In the cutoff region, as it was mentioned earlier, that base current is going to be zero. So once you make a base current as zero, as you can see in the circuit diagram, to make base current as zero, we need not apply any voltage here. Namely, here we used to have a supply voltage as a VBB. Now you can see here the supply voltage has been removed. There is no voltage applied here. So this is kept open. So there is no current flow here. The IB is going to be zero in this circuit. Okay, so that is the condition to operate BJT in the cutoff region. However, there will be the collector power supply VCC will be applied, and that causes the leakage current to flow between the collector and the emitter. The leakage current is labeled as ICEO. Okay, so the current flowing from collector to emitter when the base is kept open. If we write it here, the notation, the current what we are planning to discuss here is ICO. This is the current flowing from collector to the emitter when the base is kept open. So this O indicates here base terminal is open. Base is kept open. Okay, so that such a current that is flowing from collector to the emitter is called ICO. Okay, this current flows from collector to the emitter. Okay. So, to operate the BJT in the cutoff region, we should make base current as zero. IB is going to be zero. The transistor will be in the cutoff region, and that's what its operation that is shown in the circuit. So the base lead is kept open. The base lead is how do we make base lead open? That means we need not apply any voltage between the base and the ground, and that results in the base current to be zero. Under this condition, let us see what happens. Under this condition, there is a small amount of collector leakage current that is called ICO, because we already reverse biased the collector the base junction. So with the help of this power supply, you can see this is the NPN transistor. N goes to the positive polarity of the battery. So therefore, the collector base junction remains in the reverse bias. So the only current that flows between the collector and the emitter is the leakage current, small amount of leakage current that is labeled as ICO. And that's because of thermally produced carriers. So thermally generated carriers, because in the reverse bias, as we apply this voltage VCC, that creates thermally generated carriers in the reverse biased junction between the collector and the base, that creates leakage current called as ICO. Okay. Now, when the ICO, if you neglect it, then the VCE becomes equal to VCC. Whatever the voltage here, when the current is very small, and this is if this is going to be neglected, then the VCC, the VC is nothing but voltage between the collector and the emitter. This voltage becomes equal to the supply voltage itself, because current is not flowing. This current is neglected, that is flowing through the RC. Then the supply voltage becomes equal to the collector emitter voltage. That's what we have mentioned here. In the cutoff region, base emitter nor the base collector junctions are forward biased. Both of them are not forward biased. So both junctions remains in the reverse biased. The junction between the collector and the base. Okay, so this is reverse biased, and the base emitter junction is also reverse biased, which is zero. So this is also reverse biased. This is the status in the cutoff region. Both are reverse biased. And the subscript already we told about this. The CO subscript for the current here is it's a current flowing from the collector to emitter when the base is kept open. Okay. So this is the diagram that, which shows that the BJT operated in the cutoff mode. Okay. Now let me move to the next one, which is saturation. Another important region to be understood in the bipolar junction transistor is the saturation region. We know that in saturation region, both the collector base junction, CB junction, and base emitter junction, both are in forward biased. Okay, let me write forward bias as FB. Both are forward biased. Okay, so though here we start with the base emitter junction when it is forward biased, let us see how the base current, the variation leads to the increase in the collector current. So in the saturation region, what we are trying to do is, we know that base emitter junction is forward biased. The base current is increased. If you increase the base current, what's going to happen? Accordingly, the collector current also increases. Okay, as we know that the equation IC is equal to beta DC times IB. I'll write here once again. IC equals beta DC times IB. According to this equation, in the forward bias, as IB increases, the base current increases. Okay, that leads to the increase in the collector current according to this equation. So increase in the IB increases the collector current according to this equation. Okay. But let us see what will happen to the collector emitter voltage. So collector emitter voltage is given by this equation. This equation can be easily obtained by applying the KVL to this loop. So we have a circuit to show in saturation. I'll just project it here. So here is a circuit that shows the BJT is operated in the saturation region. If we apply KVL from this, starting from VCC, what we obtain, let me write it here. So we have a minus VCC. So starting from here, I apply in this way. So minus VCC plus IC times RC. We are moving in this direction. IC times RC, that is the drop across RC. And there is a voltage developed across collector and emitter. That is nothing but plus VCE, which is equal to 0. If you rearrange this equation, you get equation which is shown here. VCE equals VCC minus ICRC. So you can obtain this equation by applying KVL to the collector emitter loop shown here, right? So with that, let me. I assume that now you are aware of the equation shown here. All right, so fine. So now we have this equation VC is equal to VCC minus ICRC, and let us take the same equation over here. So as we said already, in the in the forward bias, as base current increases, okay. So right here. Okay, as base current increases, increase in the base current increases the collector current. But what will happen to the collector emitter voltage? According to this equation, VCE equals VCC minus IC RC. This is the equation that we have shown by applying KVL. As IC increases, the IC RC drop also increases, correct? IC increases because RC is a fixed value. Therefore, the product of IC and RC both keep increasing. Since VCC is fixed here, this is supply voltage. We are not increasing proportionately according to the collector current supply voltage. So therefore, VCE keeps decreasing, right? Okay, so let me repeat it what I said here. In the forward bias, base emitter junction is in the saturation region. The base emitter junction becomes forward biased. Now with that, if we increase the base current, that increases the collector current. Increase in the collector current increases the drop across RC. That's ICRC increases. But supply voltage VCC is fixed. It's in relation with ICRC. We are not increasing the supply voltage, doesn't increase. So VCC is fixed. Therefore, fixed minus increase in the drop results in drop in the collector emitter voltage. So the collector emitter voltage decreases. So what I want to conclude from this one is, as base current increases, collector current increases, collector emitter voltage decreases. So that means voltage between the collector and emitter in the circuit that is shown here, the voltage across this keeps decreasing. So that means earlier this voltage was reverse biasing the collector base junction. Now as this VC keeps decreasing, so slowly the collector base junction is going to become forward bias. At some point, the collector base junction becomes forward bias. That's what we want to convey from this. Okay. So this is shown in the figure. When VC reaches its saturation value, when VC keeps decreasing, at some point, it reaches saturation, and that is called as VC saturation. So when the transistor reaches, by decreasing the value of VC, when it reaches the saturation voltage, that's the point where the increase in IC will not increase in base current will not cause the increase in the collector current. Okay, we have shown this equation, IC is equal to beta IB. This equation, what I'm talking, is valid only in the active region. Okay, once the transistor reaches the saturation, as I already told, by decreasing the VC, once VC becomes equal to VC sat, the transistor is in saturation. The equation that is shown here, IC is equal to beta DC into IB, this is called active region equation, and this equation becomes invalid. That means once we say this equation becomes invalid, increase in the base current will not cause the increase in the collector current. That's what it happens in the saturation region. So in saturation region, okay, once let's assume that the BJT has reached a saturation region, and BJT is in saturation, okay, increase in the IB value, okay, IC is not going to increase. IC remains constant. IC is not going to increase according to this relation. So this equation IC is equal to beta DC times IB becomes, it's not a valid equation in the saturation region. Okay, and this we can make out in the knee region of the collector curves that's already shown. Okay, there's very few volts. VC sat is going to be very few volts. It's maybe 0.1 or 0.2 volts. Very small value of VC sat. The transistor reaches saturation. Okay, that's how the saturation region is interpreted. Okay, the same thing is explained here once again. As base current increases due to the increase in the base power supply, that causes collector current to increase, and in turn that leads to collector emitter voltage to decrease. Okay, and because of increased collector voltage drop, so when the transistor reaches saturation, IC can increase. IC doesn't increase further regardless of the value of increase in the base current, and since that shows that base emitter and base collector junctions are going to be forward biased. So this is the condition for the for the saturation region, and circuit setup to operate a transistor in the saturation region is shown here. So as you can see in this circuit, VBB is varied, and corresponding IB increases. Increase in IB increases the collector current. Collector current increase drops the collector emitter voltage. So transistor moves from reverse bias to forward bias. So therefore this junction and this junction both remains in forward bias condition. This is a situation for the transistor to operate in reverse bias. Once both junctions are in forward bias, variations of base current will not lead to the increase or decrease in the collector current. As we already mentioned, that IC is equal to beta IB in saturation becomes invalid. Beta DC times IB becomes invalid. Okay, so that is the saturation region. Okay, one thing we have to make it clear from this is, in saturation region, both junctions are forward biased. increase in base current will not lead to the increase in the collector current. Okay, so that is the condition for the transistor to operate in saturation region. Okay, with that, let me move to the next important topic to be discussed is DC load line. What do you mean by DC load line? So far, we discussed about two important regions. One is cutoff region, other one is saturation region. We mentioned that to operate BJT in the cutoff region, we have to make the base current as zero. And the saturation is the one which decreases the collector emitter voltage, and it forward biases both the junctions. Here, it reverse biases both the junctions. So we are seeing two extreme limits of BJT. And with the help of this DC means a direct current load line, we can understand, a better way the cutoff region and the saturation region. Okay, that can be illustrated with this characteristics curve. As you've seen here, this is once again the blue color lines. What you are seeing, they are going to be a family of curves of collector characteristics. And the pink color line that is shown is the DC load line. So this is a DC load line. A DC load line which is drawn from the circuit under DC condition. DC load line. What is that equation? Okay, we already discussed the equation here. This is the equation VCE equals VCC minus ICRC. Let me rewrite the same equation here. VCE equals VCC minus IC times RC. This is a standard equation which gives the collector emitter voltage across the bipolar junction transistor. And this is a line, okay, which is a straight line. Okay, so this line will tell us, the points on these lines will tell us, which region the BJT is operated. The one extreme point you can see that there is a saturation region, and other extreme point you can see there is a cutoff region, where in the cutoff region we said both the junctions, CB junction and base emitter junction, both are reverse biased, whereas here in this saturation region, both the CB junction, base emitter junction, both are forward biased. And here the remaining points are nothing but they are the points, where the active region is in play between this saturation to the cutoff. And these are the family of curves which intersect the load line, where the pink color line intersects with the blue color line. That shows that with that corresponding the base current, the device conditions match the circuit conditions. Okay, so this DC load line is drawn based on the circuit conditions, which is defined by this equation. And this equation is nothing but a straight line equation, of course. So if we can map this equation to this curves, so I can rewrite this equation in the form of y is equal to mx plus c. Okay, so y in this case is going to be the y variable is IC, x variable is going to be the VCE. So here we have x variable is here and y variable is here. Let me rearrange this equation and write IC equation. IC equation equals okay, so minus 1 by RC times VCE plus VCC by RC. So the same equation, if I call this as equation 1, and if I rearrange the terms of this equation 1 in terms of IC, I get this equation 2. Let us call this as equation 2. So from equation 1, after rearranging, we got an equation 2. Why did I do like this? Because I'm trying to make this is a straight line equation. Straight line equation 1 represents a straight line. So therefore I rearranged this equation according to this variables here, y and the x variable here. So y is nothing but IC, and you can see here there is an m here. M is nothing but which is 1 over RC. X is VCE here, and the C is nothing but VCC by RC. Now I have rewritten this equation according to this y is equal to mx plus c. Now to plot this equation on this family of curves or collector current characteristics, to draw this line on this characteristics, we need to have a 2 points to plot this line. So to obtain one of the points, you can make other point as 0. Namely, if I want to obtain point on the y-axis, I have to make x as 0. X is nothing but VC. Let it here. So if we assume from equation 2, if VC is made 0, VC is nothing but x, I get a point on the vertical axis. If VC equals to 0 in this equation, IC becomes equal to VCC by RC. Therefore, let us call this point as an A. This is the point on the vertical axis. X is 0 because x is nothing but the VCE, but there is a y value which is VCC over RC. Similarly, to obtain a point, this point I will call as A point. Okay, another point let me call as this point as B point. So if I make IC as 0, I will get a point along the x-axis. So in this equation 2, if we make IC as 0, so VC becomes equal to VCC. So let us call that point as B. And now we have x value as VCC, y value is 0. So we had now 2 points now. One point is A, whose coordinate are 0, VCC by RC. This coordinate is 0, VCC over RC. And the point B as a coordinate of VCC, 0. Joining these 2 points defines this equation 2. So now this equation 2 is as per the line defined by equation 2 is as shown here. Okay, so this line works according to the equation 2. So we obtain namely the 2 points A and B. Now based on these 2 points, we can decide the saturation and the cutoff region here. So VC is equal to VCC, where both junctions are reverse biased, is going to be the cutoff region. So in other way, we can say that in cutoff region, base current has to be 0. So exactly once you make base current as 0, the curve is lies on the x-axis. So therefore, this point defines the cutoff region. This extreme point defines the cutoff region. Other way, we have saturation region, where in which we have IC exists, but VC is going to be 0. So this is a point, saturation point. At saturation point, the collector current value is VCC by RC. Okay, so in this way, the active region and saturation region and cutoff region can be defined. On the DC load line, this is a pink color line, what it is shown. Above this line, if you move along the pink line above, that shows it is a active region. And if you go extreme point, you reach a saturation region. And if you move downwards, again it gives an active region. Okay. Now the load line will decide, where is the cutoff region. One end of the load line gives the cutoff region, other end of the load line gives the saturation region. Between the load line, there is going to be the active region. Okay. So in this way, the DC load line helps us to categorize the active region and the cutoff region. Okay. So that's going to be the DC load line. Now let us take a problem and try to answer the concepts of this problem. So example is 4.4. We need to determine whether or not the transistor is in saturation, assuming that saturation voltage is going to be zero point 0.2 volts. So this is a circuit diagram given to us, and based on the circuit diagram, we have to decide whether transistor is operated in saturation or not. So the base power supply given is 3 volts, RB is 10 kilo ohm, RC is 1 kilo ohm collector resistor. Beta DCFA transistor is given as 50. Collector power supply is 10 volts. With all these given values, and saturation collector emitter voltage is 0.2 volts given, we should check whether the transistor is really in saturation or not. Let us solve the problem, go step by step, and try to answer the question asked here. Now let us go and determine the IC saturation. We already know the equation of VCE. I will rewrite once again. Just now we have derived it by applying the KVL. VCE equals VCC minus IC RC. VCC minus IC RC. So if I assume that IC as IC saturation, this as IC saturation, the VCE becomes VCE saturation. VCE saturation. So now the new equation for IC sat, if you rearrange this, that becomes equal to VCC minus VCE sat divided by RC. I'm sure that you can easily derive this equation from this one. So let us determine the saturation collector current, which is given by VCC minus collector emitter saturation voltage divided by the RC. Let us substitute the values. VCC is given as 10 volts from the circuit. VC saturation is 0.2, RC is 1 kilo ohm, and simplifying this, that gives me saturation collector current as 9.8 milliampere. Now let us see that whether the base current is able to produce this much amount of saturation current or not. Okay, so let's try to find out the base current. So this also can be obtained by applying KVL to the base emitter circuit. If I have a doubt, let me apply here. This is a base emitter. If we apply a KVL for this group, minus VBB plus the current flowing through this, let me take it as IB. Now I need to take a drop across RB, which is IB times RB, and here we have a voltage which we should not forget it. This is the base emitter voltage, so that comes into the loop VBE, that is equal to 0. I just want to obtain the base current from this one. So base current is, retaining the base current, this gives me VBB minus VBE, that is in the numerator, divided by RB. So this is how we can obtain the equation for the base current. You can see same equation is here now, VBB minus VBE divided by RB. Now we can substitute all the values. VBB is 3 volts base power supply. Base emitter voltage is 0.7 volt for silicon transistor. Base resistor is 10 kilo ohm. Substituting all these values and simplifying gives us IB as 0.23 milliampere. And let us substitute that in the equation. IC is equal to beta DC times IB. Beta DC is defined as 50 and the IB is 0.23 milliampere. That gives us 11.5 milliampere. Now we can make out that here. So transistor is in saturation now, that we can easily decide, because we already know IC sat is going to be 9.8 milliampere. Okay, the saturation current is already 9.8 milliampere. This shows that the specified beta DC, the base current, is capable of producing IC greater than IC sat. The transistor is it's going to be in saturation, and the collector current is going to be, value is going to be around 11.5 milliampere, which is never reached. So it is stuck up in the 9.8 milliampere. So this value is 11.5 milliampere is not reached. Therefore, we can say that transistor is going to be in saturation. Okay. So with that, let me move now to the next topic of discussion is a beta DC value. Let us see that how beta DC is dependent on other factors. Beta DC is also called as an HFE, as it is defined forward current gain. HFE stands for the hybrid parameter forward current gain. That can be called as beta DC. We know that beta DC is going to be the IC by IB. It's a ratio of IC by IB. And it's an important parameter, BJT parameter, that we need to examine and also look at whether beta DC is dependent on any other factors or not. So beta DC is not a constant. It depends on several factors. First and foremost is it depends on the collector current, and also it depends on the temperature. As collector current increases, beta DC also varies. Let us see that on how the beta DC depends on the collector current and the temperature. And we assume that here junction temperature is kept constant, and increasing IC also causes the beta DC to increase to a maximum value. As we can see in the graph here, we can make out clearly that from the graph, okay, the x-axis is going to be the collector current and y-axis is going to be the beta DC value. Okay, as collector current increases, as we can see that the beta DC, let's assume with some temperature, let's say the room temperature is 25 degrees Celsius. If I assume this curve at 25 degrees Celsius, we can see that collector current as it is smaller, the beta DC is lower, and as collector current increases, you can see that the beta DC also increases and it goes for higher value, and further you can see that as collector current increases, the beta DC decreases. We can conclude that for lower collector current and higher collector current, the beta DC is low, and at some point of collector current, say for example 10 milliampere, 10 to say 15 milliampere, the collector current the beta DC is going to be the maximum value. So when the collector current is in the range of 10 to say 15 milliampere, the beta DC is going to be maximum. That's how the collector current varies with reference to the beta DC. And we can also see if I maintain the collector current as a constant, assume it, let's say that collector current is kept fixed at say 10 milliampere, and varying the temperature. We can see here as temperature starts decreasing, okay, the beta DC also decreases. As temperature increases, beta DC also increases. So this is a factor where the collector current is kept constant, but only the temperature is changing. Earlier we have seen that temperature is fixed. When the collector current is changing, for smaller collector current and for the larger collector current, beta DC is lower. And for some value of collector current, beta DC is maximum. But here, when the collector current is fixed, let's assume that we are fixing collector current at 10 milliampere. This is the value, fixed value. Now, as temperature keeps decreasing, the beta DC also decreases. And as the temperature keeps increasing, beta DC also starts increasing. The x-axis, the y-axis here shows the value of beta DC. The x-axis is going to be the collector current. So we have shown how beta DC varies with temperature and beta DC varies with collector current. Okay, now let's go to the beta DC is not at all depend only on these two parameters. It also depends on the transistor. There are a lot of inconsistencies in the manufacturing process. Therefore, if we select two transistors, then beta DC of two transistors will be different. That we can easily make out when you pick a two transistor from the manufacturing lot. Two transistors will have a different beta DC values. Okay, so now generally the manufacturer specifies minimum beta DC in the data sheets, and we also shown here beta DC depends on temperature, beta DC depends on the collector current. So that's about the beta DC. Now let's move to the next topic called as maximum transistor ratings. This topic is important because the transistor region of operations we are estimating from this topic. Generally, transistor bipolar junction transistor comes with different power ratings. Manufacturer generally specifies the PD max. PD max means it's a maximum power dissipation. PD max. So it is nothing but maximum power dissipation. How much the transistor dissipates the power that is decided, that's given by the uh, manufacturer. Excess heat generated will destroy the transistor. Therefore, one should be careful while providing the voltage and current. Because the PD max itself depends on collector emitter voltage and collector current. The formula for PD max is it's a product of collector emitter voltage into collector current. That's how the PD max can be estimated. Okay, the PD max is a product of collector emitter voltage and the collector current. This rating is important because this rating will decide what must be the collector emitter voltage, what must be the collector current to be applied for a transistor for its safe operation. If voltage or current exceeds this PD max, the applied voltage or applied current exceeds the PD max, then we are in unsafe region of a transistor. With that, here is we have a formula here. If I assume that since there are two variables in this equation, VCE and IC, if we assume VCE is maximum, then we can estimate what must be the collector current so that the PD max and VC is not exceeded. So that can be estimated using this relation. This relation assumes that collector emitter voltage is maximum, and from that we can estimate what must be the collector current. In another way, if IC is going to be maximum, in this if I make assume that the collector current is at maximum, then we can estimate collector emitter voltage for safe operation so that this doesn't exceed this ratio PD max by IC. So these two relations plays an important role in deciding where one should operate transistor safely. Okay. Now let us go through typical example and try to understand from the graph how one should operate the transistor. Here in this graph, we can make an observation from this graph. There are a couple of points which one need to pay attention. There are points at which IC max. If I assume that maximum collector current as 50 milliampere, then I must have VC should be chosen such that it will not go beyond this A and B points. These are A point A is one here, point B is another point. Let's assume that the PD max given is 500 milliwatt. If this is going to be the maximum power dissipation given for the transistor, then we should ensure that the product of this VC and IC should not cross this limit. If that is the case, if PD max is 500 milliwatt, and if assume that maximum collector current is 50 milliampere, then the collector emitter voltage should be in the range of A to B. Okay. All this gray color region, whatever it is shown here, shaded region, that is unsafe region for the BJT to operate. So it starts from here, and we have a power dissipation graph here, pink color graph, and from here it is a constant. This is all shaded portion, this region, and above this region is unsafe for the BJT. This region is unsafe. The only region which is safe is going to be the white color portion here that is shown. This is safe for the BJT to operate it. So we discussed about the points A and B. Assuming that IC or collector current is at maximum, then the one should ensure that the BJT VC should not exceed the points A and B, A to B. It should not cross the B. And next one is going to be the right. Okay. The next one is going to be the PD max between the B and C. The curve follows this equation. PD max is equal to VC into IC. The product of that is nothing but it is this curve between the B and C. So between B and C, the curve follows equation PD max equation. And we already said about this. Between point A and B, IC is maximum, and therefore it follows equation. Let us call this as equation 1 and this as equation 2, so that we can easily understand it. So equation 2 is followed between the points A and B, assuming that IC is maximum. And between the points C and D, equation 1 is followed. Because here we assume that collector emitter voltage is at maximum. We already said about that. When VC is maximum, one can estimate the collector current for safe operation. If IC is maximum, so we can estimate collector emitter voltage for the safe operation of the BJT. If VC, IC both are variable, then we should not exceed the PD max. So 3 equations are used here. This is, let us call this as equation 3. And as per that, we have here the curve here. Between the points C and D, equation 1, wherein which it assumes VC is maximum, IC should not exceed the points C and D, this region. It can't exceed this region. That is equation 1. When both VC and IC are given, it should not exceed this region. So the curve here is following PD max equation, which is nothing but equation 3. And when the IC is maximum, the VC should not exceed the points A and B. It should be within this range. Okay. So if it crosses that, then it becomes unsafe for the BJT to operate it. So that's about the maximum power dissipation curve, and the values which are tabulated here, which will show you that product of VCE and IC should not cross 500 milliwatt. That is the maximum power dissipation defined by the manufacturer. Okay. If we cross this equation, if you have a question like what happens if I cross this points C and D, you are violating this 500 milliwatt, and that leads to unsafe operation of the BJT. Okay. So product of 10 volts and 50 milliampere gives me 500 milliwatt. Product of 15 volts, 33 milliampere gives me 500 milliwatt. Product of 20 volts and 25 milliampere gives me 500 milliwatt. In that context, so we are not exceeding the maximum power defined by the manufacturer. Either I can have IC value smaller or VC larger, or VC value smaller, IC value is larger. And we should ensure that the product of this should not exceed 500 milliwatt. Okay, we also made each one variable as a constant and seen that what should be the other variable limit. Here we made the VC as maximum and estimated the collector current to operate, which is nothing but C and D. Here we made the IC as maximum and estimated the collector emitter voltage. It is in the range of from A to B. Okay. And here we have both variables PD max. PD max follows this bent region, arc type of region, and any current and voltage falls above this arc, which is unsafe. In that way, this graph helps us, to think about the BJT operation, the safe and unsafe regions. So, the gray color is unsafe portion, and white color is the safe portion for the BJT to operate. Okay. So we have a couple of problems here to work out on the maximum power dissipation. Let's take example 4.5. A certain transistor is to be operated with a collector emitter voltage of 6 volts. If its maximum power rating is 250 milliwatt, what is the most collector current that it can handle? Very simple problem. We have to estimate here. Collector emitter voltage is given as 6 volt. Maximum power rating is given as 250 milliwatt. That's a PD max. And we should know what must be the collector current to handle the transistor safely. It is straightforward. We already know PD max is a product of VC and IC. I want to derive here for collector current. Collector current is PD max, maximum power dissipation by the collector emitter voltage. So maximum power dissipation is given as 250 milliwatt. That's numerator, and the collector emitter voltage is 6 volts. The ratio of this gives me 41.7 milliampere. So if I provide collector current of 41.7 milliampere, so the transistor is going to be safe. So this is the maximum current for this particular value of collector voltage. Collector voltage is 6 volt. For 6 volts, the collector current of 41.7 milliampere is a suitable value. The transistor can handle maximum collector current if VC is reduced. In case if you want to reduce VC, then collector current can be increased. As long as we are not violating the product of the ratio of the PD max by IC max, so that should not exceed PD max or IC max. The values should not exceed. So that's the example 4.5, and let's move to the example 4.6. In example 4.6, the transistor in figure 4.19, this is figure 4.19 given, as the following maximum ratings. Maximum power dissipation is 800 milliwatt. Maximum collector emitter voltage is 15 volts. Maximum collector current is 100 milliampere. And we need to determine the maximum value to which VCC can be adjusted without exceeding a rating. Which rating would be exceeded first? I think you must have understood the problem with this time. So VC max is given, IC max is given, PD max, all data ratings have been given here for the circuit which is shown. And we need to determine the maximum value. The VCC can be adjusted without exceeding the rating defined here. The VCC is nothing but this supply voltage to be applied so that we are not violating this ratings given. And which rating should be exceeded first? So we'll see that which rating will exceed first, whether the VCC or the product of this which will exceed first. We'll see that. Okay, let's solve the problem. So this is the given circuit. Base power supply is given as 5 volts. RB's base resistor is 22 kilo ohm. Collector resistor is 1 kilo ohm. Beta DC of a transistor is 100. And VCC which we have to estimate it. Let's solve the problem. First is let us find out the base current so that one can determine the collector current. So we already know this equation by applying KVL into the base emitter loop. That gives me base current as VBB minus VBE divided by RB. Substituting the value of VBB, VBE and RB gives us base current as 195 microampere. The current that is flowing here is 195 microampere. That is the base current. Okay. From this we can estimate the collector current. IC is equal to beta DC times IB. So beta DC is 100, IB is 195 microampere. That gives us collector current as 19.5 milliampere. The current that is flowing here is IC, which is equal to 19.5 milliampere. So IC is very much less than IC max. IC max is 100 milliampere. This is 100 milli given. IC now what we got is 19.5 milliampere. So this will not change the VCC value, of course, because VCC applied will be nominal value itself. It is determined by only IB and beta DC. The voltage drop across RC can be estimated, VRC. The voltage drop across this can be estimated. Once we know IC value, this IC and RC can be, product can be estimated, and we can estimate what is the voltage drop across RC. ICRC is the voltage drop across RC. That gives us voltage drop as 19.5 volts. Now we can determine the supply voltage should cater whatever the VCC that is applied here. Though we don't know the value here, that must provide a VC value, VC max of this, and ICRC drop of this. We already know ICRC drop, which is 19.5 volts, and now we can estimate. Okay, so we can determine the VCC and VC from this. Okay, VC minus VC max, that gives me uh, uh, to determine the VCC. We can add up those two together. 15 volts is going to be the uh, VC max, and VCC, I mean the VRC is going to be the 19.5 volts. That gives us VCC as 34.5 volts. So now VCC is going to be the 34.5 volts. That is within our existing conditions, VC max. So that's going to be the VC max is going to be 19.5 volts. Okay, so now whatever the defined value, let us calculate the product and whether that product of VC max and IC exceeds our power dissipation of 800 milliwatt. So VC max is 15 volts and IC is going to be 19.5 milliampere. That gives us 293 milliwatt, but the PD max is going to be 800 milliwatt. So the power dissipation 293 milliwatt has not exceeded the 800 milliwatt. So therefore, even the supply voltage VCC is 34.5 volts. What we got. So VC max is going to be 15 volts. Is limiting rating in this case. So the base current is removed using the transistor to turn off. So VC max will exceed first, then because the entire supply voltage depends on the VCC. Depends on entire supply voltage VCC will be dropped off across the transistor. So this is a reason provided here for the which one exceeds first here. So VC max will exceed first because of the supply. This is going to be very small value. So that is the one which highly depends on the VCC. Therefore, it exceeds first compared to the other power dissipation value. Okay, so that's about the power dissipation. And next is going to be the derating, the power derating. The maximum power dissipation is depends on the temperature, which is at specified generally at 25 degrees Celsius. For higher temperatures, we should look at the data sheets. So let us see that on how the derating factor is determined. Generally, derating factor is given in terms of the positive or negative. Here it is going to be 2 milliwatt per degree Celsius. That is going to be the derating factor. Okay, so based on this, we can estimate the power dissipation at other temperatures also. That's where the derating factor helps us. So the maximum power dissipation reduces. This shows that for every degree Celsius increase in the temperature. Okay, so as temperature increases, the maximum power dissipation PD max decreases. Okay, this is a negative temperature coefficient that it has got. Therefore, as temperature increases, the maximum power dissipation decreases. At what rate it decreases, it is given by the derating factor. Per degree Celsius increase in the temperature drops the maximum power dissipation by 2 milliwatt. That's the derating factor determined here. So this is about this. There's one problem related to the derating factor. I think the students can solve this on their own, and then followed by we have a BJT data sheet, and next we'll go to the important topic called as voltage amplification. I think this we need to cover up in the next class, and followed by we'll introduce the BJT part is completed. We'll go move on to the field effect transistor part, and that's all for today's class. If there are any questions, I can take up this on this topic that we have covered. Any questions? Okay. If there are no questions, I will stop at this point and continue next class with BJT as an amplifier. Thank you all.